okay, the quiz using the Teams. Any problem, guys? So any problem using the Teams? So before we start, so our midterm also, I will try to use the using the Teams also. So for that, let me know if you have any problems. Okay, if using the team, so maybe I will change another technique lah. But normally I will use the team. So sometime so on the previous student, so they have a delay. So depends on your internet. Okay, internet speed lah. Depend on the speed. Maybe so when we start at 10 o'clock, for example, 10 o'clock. So maybe it will be appear this message or the file will be appear at 10 minutes, something like that, 5 minute delay lah. So they have some delay, don't worry. So I think the depends on your internet lah, internet speed. So maybe no delay, but some of the student before this, they have some delay around, I think the most is around 10 minute delay lah, around the 10 minute delay. That's why we try to start our midterm, okay, our midterm test, so will be earlier. Okay, so that okay, I will set earlier lah, so that it can be you can get the message from the team that you have for example, you have the test, so you can okay, you can access the Teams, then you can download the the question lah, using the Teams. Okay, from Teams you can download, then you can answer lah. So any problem, guys? Okay. Okay, so any problem? So using the Teams. Okay, if you have any problem, so let me know. Let me know. So some of the not our class. So some of the lecturer will be used the ULearns. Okay, some of the lecturer, another lecturer lah. So I'm not sure. So but the time will be same. The time will be same. That's why we have to set. Okay, that's why we have to set the exact time lah. Exact time lah. So for all the student will be take this subject. Okay, so but the platform is a difference lah. For me, I prefer to use the Teams. Okay, so because I'm familiar with using the Teams, so that's why. Okay, if you have any problem, for example, we run for the quizzes for the quiz before this last week. So any problem? So maybe some of you cannot send because of the this is I'm sure some of you late to upload the question, the answer. So that's why we cannot. So the team is very fixed. So for example, I just said at 10 will be closed. So at 10 will be closed lah. So you cannot upload your answer. Okay, you cannot upload the answer lah. So that's why you have to upload early. Okay, so that's why this is some of the the time lah. That's why we set, okay, normally for the final or for the midterm, so we give some extra time lah, so that you can capture the image for your answer, then you convert into file, then you upload to the Teams. Okay, so regarding to the midterm test, so midterm test that I mentioned to you, so on 6 May, okay, on 6 May, okay, at so you use the Teams. Okay, so it's 8:50 p.m. So okay, 1.5 hours. Okay, so the chapter will be covered for chapter 1 and chapter 2. Okay, until the chapter 1 is the introduction to numbering, and numbering systems, okay, and codecs. And chapter 2 will be logic gate and the Boolean algebra lah. Right, so that is the topic will be covered for the midterm test. Okay, so for the midterm test, so make sure when you take the picture, okay, make sure your answer very clear lah, very clear. So easy to me to mark your answer. Okay, make sure you take the picture for your answer. Make sure all the answer will be in the one page. Okay, to make sure all you can read the your handwriting, so make sure I can read lah. So if you can read, so that means I can read also. So make sure. So if your picture is blur, so maybe you can take another picture. Then you can combine into one file. For example, maybe first you can put on the on the words, okay, put on the word all the answer, question number 1 and question number 2 and so on. Then you can export to PDF. Then from the PDF you upload to Teams lah, right? So because if you okay, the upload using the word, so maybe the file is too big, so will be take time, depends on your speed. So that's why when you upload, okay, sometimes almost near to, for example, near to expired, so sometimes it will be so it cannot capture. That's why you have to upload early lah, so that it can be appear on your Teams, okay, in the Teams lah. And then if you convert export to the PDF, so maybe the file will be reduced, the size of file will be reduced lah. That's why as first maybe take the picture and then convert into the words. Okay, maybe some of you have the apps, okay, maybe using the cam scanner. Okay, you can use the cam scanner, so that means convert from your image to PDF. Okay, up to you. And please make sure before you submit, okay, check your name. Okay, make sure you have to put your name in the answer. Okay, in the answer script. Make sure you put your name. No metric is okay lah. But it also you can put the names and metric number lah, so that I can know this is your, okay. Because when I download all, okay, download all the files, so it quite tough for me to detect if you not write your name in the answer script. So I will back, so to get the file name who's the answer script. That's why on the answer script, make sure you write your name, okay, write your name and metric number, then you can write the answer lah. Okay, make sure you can read the when you take the picture, so make sure you can read lah. So if read, that means I also can read lah. Because before this, so some of the students submit before this, the image is blur, so it's quite tough for me to read and to mark your midterms test or final, something like that. So make sure, so when you take the picture and then before you submit, all right, so make sure check your answer first. Then sometime, okay, the previous this is the previous, I think, on the previous student, so they are not submitted the complete, okay, the complete answer. All right, so that will be missing lah, will be missing when I mark. So this student is very good because of for example, okay, so they have the 4 questions, so the 3 questions will be almost get the full marks, but not this student not answer the question number 4. So I just I asked this student, so you not answer the this student mentioned to me, so they answer the all, but when they check the answer, this means the question number 4 will be missing. So that's why before you submit, okay, before you submit your upload your answer script on the team, so make sure you check question number 1, okay, all the answer script, then you submit, okay, then click the submit button lah. After all everything is okay, then you click submit. Right, so okay, so that's all for reminder, soft reminder for the midterm test. So if no problem, so I will start the chapter 3 part 2. Chapter 3 is the functions of the combinational logic lah. Okay, so when we combine the logic gate, so this combination will be have some function lah, some function. So and then the function we can be generate the application lah, right? So this is will be covered for the chapter 3 part 2 lah, combination function of the combinational logic. Okay, so this is our contents. Okay, so we try to finish for today. Okay, try cover until 3.8 if you have the time. All right, so on the function, okay, for the combinational logic circuit, so we have the adder, okay, we have the comparator, we have the encoder, we have the decoder, and then actually this is a component lah, okay, from combination of the logic gate we can create the component of adder. That's why adder, the function of adder to add or to do some submission of the binary number, for example. Then comparator. So this comparator actually is some component that we can use for compare. For example, that comparator we can compare the binary number, binary digit. All right. So and then we have the encoder, decoder. All right. So multiplexer, demultiplexer, and then so combination of this one we can apply to the system. For example, like flip flops. Okay. We have the quanter and so on. So this is component on the combinational logic. Okay, Right. So for introduction, so we are mentioned to you. So we are focused on the MSI, is the medium scale integration. That means our logic gate from 12 to 99 lah. Okay, sure. So this is our normally in our topic we cover until medium scale integration. Medium scale integration, that means combination of the logic gate around 12 to 99 equivalent gates on the chip. Okay. So they include the logic function such as a counter. Okay, this is a application of the combination of the logic gate. So we can use as the counter, shift register. We can use the arithmetic logic circuit, encoder, decoder, comparator, multiplexer, demultiplexer, and the combination and sequential logic circuit lah. Right. So the advantages of such device include the lower cost, higher reliability, and design simplification of the complex logic system. Okay, this is some introduction for function of the combinational logic circuit. So that I mentioned to you. So we are focused on the medium. So actually we have also the small scale integration, small scale around until 11 gate. So we focus on the until the medium scale. The medium scale, that means our gates, logic gate around 12 to 99. Okay, gate logic gate. Okay, so we go for the function number one is the adder. So adder is the we can call it as the summer. Okay, or adder is the digital circuit that perform the addition or of numbers. So that means this adder we can perform for additional of battery of the digital number. For example, 1 plus 1 equals to 2. Okay, 2 plus 2. So this is the in the digital. So for binary also you can do 1001 plus 1100. So you can use the adder to perform this additional of numbers. Okay, in computer structure or other kind of processor, the adder are used in the arithmetic logic units to calculate the addresses and tables in this and for many similar operation. So this some example application of the adder. So they used to calculate the address. Okay, so on the processor we have a lot of address. So that's why we use the adder to calculate the address and the table. Okay, on the adder we have two type of adder actually. So we have we call the half adder, and then we have the full adder. So the half adder, you can see this one, the half adder accept two binary digits on the inputs and produce two binary digits on the outputs. That means we have for half adder we have two input, two outputs. Okay, you can see the symbol of half adder here. Right, this is a symbol for half adder. That means we have two. Okay, we have two inputs and also we have two outputs. Okay, so output we can declare as the sum and carry. Alright, so you can see on the truth table here. Okay, you can see here truth table. So for example, this is the additional operation. Alright, so 0 plus 0. So 0 plus 0 actually is a sum is a 0 here. Sum is a 0. So and then also no carry. So no carry, that means also 0. And then for example here 0 plus 1. For example, input A is 0, input B is 1. 0 plus 1, so sum will be 1 here. Okay, sum will be 1 here, so this one will be 1. Alright, but no carry, so we don't carry anything. So that's why here carry will be 0. Okay, and then next you can see this one. So 1 plus 0 will be sum will be 1. Sum will be 1, but no carry so we don't carry any digit. Alright, so but if 1 plus 1, okay, 1 plus 1, so we have carry 0. Okay, sorry, carry 0 lah. So we have the sum will be 0, but we have carry 1 here. Okay, we have carry 1 here. Okay, that is the truth table for the half adder. So you have to remember. So 1 plus 1 actually we get 2. Okay, that's why you see this one, actually this is a 2 in the decimal. That's why we have sum is the 0, but we have carry 1 lah. We carry 1 here. Okay, this one we call the truth table for the half adder lah. So the half adder, that means we have 2 inputs and 2 outputs. Okay, so this is the symbol lah, symbol of the, okay. So actually the half adder, it can express as the exclusive or and gate lah, right? So you can see this one. That is the half adder. So that means we have here. So this is you can see in the slide. So actually this is inside the half adder. This one lah. So this one, inside this one we have the exclusive OR. Okay, exclusive OR and gate. This is exclusive OR and gate lah. So the exclusive OR for sum, and then for n is the for the carry lah. Right. For example, this one is 1 1. Okay, 1 1 sum will be 0. Okay, and then carry 1. Right. So that is the logic gate inside this adder lah, inside this adder. But this is okay, this one we call the symbol of adder, half adder. But the component inside the adder like this lah. So we have the exclusive OR and we have the AND. So exclusive OR for the sum, and the AND gate will be for the carry lah, for the carry. Okay, for the full adder, alright, for the full adder we have 3 inputs and then we have 2 outputs. Okay, that we call the full adder lah. So actually the full adder we actually is combination on the 2 half adder plus with OR. Okay, plus with OR gate lah. So I will show after this. So that is the full adder. Okay, the full adder, that means we have 3 input, then the output will be 2 lah. So the input will be, we have the A, B, and carry. Okay, carry in, we call the carry in, and then for the output we have sum and output carry lah. Alright, for example here, okay, this is you can see this one is the truth table for full adder. That means right, so this is operation adder. So 0 plus 0 plus 0 here. So automatically we know the sum is a 0, carry also 0. Okay, for next example here, 0 plus 0 plus 0. So automatically the sum will be 1, but no carry. Okay, carry is a 0 lah. So, okay, for example like this. For example like this, 0 1 1. Okay, 0 1 1. So that means the sum will be 0. Okay, then carry 1 here. Okay, carry 1 here lah. Alright. So that's similar with this one lah. So for example, we have 1 plus 0 plus 0. That means the sum will be 1. Okay, that means the operation will be plus. So will be plus. For example, 1 plus 0 will be 1, but no carry. Alright. For example, like this, 1 plus 0, okay, 1 plus 1 will be 0. Okay, that means the sum will be 0 and then carry 1 here. Alright. So this is also similar, 1 plus 1 plus 0. So automatically will be same. Okay, next you can see this one, 1 plus 1 plus 1. So the sum will be 1 and carry 1. Okay, so this is the truth table for the full adder. The full adder. That means the full adder, we have the 3 inputs, 2 output lah. Okay, the input we can declare as the A, B, and C, carry in. And then we have for the output, we have the sum and carry out. Okay, so this is, you can see, this is the Boolean expression for the output sum, alright. And then this is for Boolean expression for the carry out lah. Alright, carry out here. Okay, so this is you can see here is the logic gate inside the inside the full adder. So they actually this one inside this one this logic gate inside this one inside the block diagram. So that's why the block diagram of the full adder we put like this. Okay, this is a symbol of full adder. So we put this one. Okay, that's why you have to remember. So if you have something like this, you have A, you have AB, you have AB, AB. All right. So next you have the this one sum and carry out. So we know this one will be uh, half adder. This one will be half adder. Okay, if we have three inputs to output, I think this is a full adder. Okay, so you can see this one. Actually, I mentioned to you. So the full adder can be implemented with two half adder with one OR gate. Okay, you see this one. Actually, when we from this one, okay, from this equation, actually we can rearrange to be like this. So this means here is the one half adder. Okay, so this one another one half adder. That means we have two half adder, but we plus with another OR gate. OR gate for the carry out. For the carry out. So that's the this is some equivalent logic symbol. We can see this one. So this is we call the half adder one, half adder two, and then this is for sum, and this is for carry lah. Alright, so inside the full adder block diagram, something like this. Okay, we have three. Okay, A, B, and carry in, and output will be like this. So it will be appear like this. Normally inside this one will be like this. So we have the logic gate. Logic gate inside the IC. This one, the integrated circuit here. Okay, so this is some function of the adder lah. So we can use the adder for the parallel binary adder, alright, or we can use the okay, for this one for 2-bit parallel adder using the full adder, right? So okay, this one is the parallel lah. That means we combine. Okay, for example, we have, you can see in this figure here. So we have the 4-bit for the full adder. So this one full adder 1, full adder 2, full adder 3, full adder 4. Right. So you can see this one. So the n bit parallel adder can be constructed using n. Okay. So for example, if we want, for example, here is a 4 bit. This means we have to use 4 bit for full adder with the 0 carry in the on the LSB on the least significant bit. So for the 2 bits, 2 adder are needed lah. Okay, for example, this is some example. If you use 2-bit numbers, so that means we have 2 adder, full adder. This one full adder. We have to use full adder lah. The full adder are needed. If 4, that means we need 4 adder lah. We need 4 full adder will be used. Okay, and so on. So we have 8. Okay, for example, if 8-bit numbers, so that means we have to use 8 adders, full adders. Okay, so this some example lah. Some example, you can see this one. For example, we have this one is we call the least significant bit, and then this is most significant bit, right? So you can maybe I declare as the A1, A2, A3, and A4, and then this one will be B1, B2, B3, B4 lah, right? So we can do the operation this one. This is sum 1, sum 2, sum 3, and sum 4. Actually, if you have a sum here, so that's why we put another sum here. So maybe we have another carry or output carry here. So that we call the sum. This is the okay. You can see this one. So the actually is the sum file. Actually we can declare as the C out here. Okay, on this on this equivalent to C out lah actually for C5 here. Okay, so this is some example. For example, we have the 1011 plus with 1000. So you can do the operation. For example, 1 plus 1 will be 1. Okay, for example. Okay, so carry 0. So carry 0 lah. So 1 plus 1 will be 1. Okay, 1 no carry lah. So 0. 1 plus 1 will be 0. Carry 1 lah, for example. Right. So this is some example lah. Okay, so this one, for example, if you use 2-bit parallel adder, we use 2 bit full adder lah, Alright, so if that means we have to this one, 2 bit this one we call 1 bit, 2 bit, bit number lah. If we have used 4 bit, something like this, okay, something like this lah. If you have 8 bit, so we have another 4 here, okay. If you use another 4 bit, okay, 4 bit, for 8 bit lah, for example, so we have another one. So this one x5, x6, 7, 8, okay, and then connection, the key out here will be connect to carry in here and so on, okay. So but this one actually you can convert into the logic symbol lah, like this, okay. So you can see this is actually in our IC, like our IC lah. So we have the leg lah, so every leg we have the numbering, okay, numbering. So actually, so something like this we combine to be like this lah, okay, to be like this symbol, logic symbol lah. So this one we have the binary, okay, binary number for A, and then this one we have the binary number for B, and this one we have the carry, input carry, and also this is the output lah, output sum. We have the input 1, input 2, input 3, input 4, and then this is the output carry lah, okay, output carry. So this is symbol on our IC, so our IC, that means we use the for 4 bit lah, for example, okay, 4 bit. If we have 8 bit, for example, similar like this one, similar like 4, so we have 8 lah, okay, 1 2 3 4 5 6 7 8 for A, and then we have another for B, okay, another for 8, another B, and then we have the input carry, and also we have another 8 lah, another 8 for output, and also we have another one for output, output carry. So this is, for example, if you use 8 bit, okay, 8 bit parallel adder lah, that means we have to use 8 full adder lah. Okay, so this is some example on IC. Okay, you can see this IC. So this IC name, this is actually the name of IC lah. So maybe on the experiment on the lab, you can see, you can find this this IC. So for example, like 47LS283 actually is the for the 4-bit parallel adder. Okay, some example here. So you can see here is the some late here. So you can see this is late number 1, right? Late number 1, late number 2, 3, and so on lah. So you can see actually this is on the IC. You have see the this you can see the hole here. Actually, is to represent as the starting number. Okay, this and on the left. So maybe you can see this one if you have the IC. So you can see this one. So this actually is starting for the numbering lah, numbering 1. Okay, numbering 1, for example. So this is, so for example, we have our IC here. Okay, so for example, if our symbol here, okay, our hole here, so that means our starting late will be here, 1, 2, okay, 2, 3, and so on lah. Okay, and then until here will be 16. All right. Okay, so every leg we have the we have the already function. For example, for VCC, okay, so already put on the 16. Okay, for ground, for 8, that's why you have to connect to the ground and connect to the VCC to on this IC. Okay, so actually this IC is not on, so that's why you have to put the VCC. VCC is the power supply lah. So normally around 3 volt to 5 volt lah, depends on the IC lah. It's normal, it's a 3 to 5 volts. Okay, you have to give a supply to the IC, and then you have to put the ground, right? So then this 4-bit parallel adder can be functional. If you don't put the supply here, so your IC is not functional. So even you put the power supply in the on the total your total circuit. So but if this IC you don't put the supply, so your IC is not on. That's why when you do the, for example, like your assignment after this, so assignment based on the simulation assignment, so you can see if you don't put the IC the VCC, the supply, so maybe your IC is not functional because of the not supply on your IC. Okay, so this some example. All right, so like we use the 4 bit, okay, 4 bit, 4 bit for the using the 4 full adder. All right, so similar like before this. Okay, so for example, we have the 1001, and then another one will be so 0011 lah. So the operation like this. So 1 plus 1. Okay, actually the initial will be 0. Okay, so initial for the carry in we put as a 0 here. So as a 0. Okay, so 0 plus 1 plus 1. Okay, 0. The sum will be 0, and then carry 1 here. Carry 1 here. Alright, 1 plus 0 plus 1 will be sum will be 0. Carry 1 here. Right, so 1 plus 0 will be 1, carry 0, no carry, okay, just 0. Okay, 0 plus 1 plus 0 will be 1, carry 0 lah. So that means the output for C4 here will be 0. Okay, so here actually is the value 0, 0, 1, 1. Okay, that means will be 12. Okay, so this one is the 8. Okay, so this is 8 plus 4. This one 2, 1 lah. So this means the total on the decimal will be 12. Will be 12. So that is the how it the function of the adder. All right. Okay. So next we have the adder expansion. So this means we have more than for example more than 4 lah. That means we need 4-bit adder. So that means we need 4-bit we need 8-bit adder. That means we have to combine 4-bit adder to be 2-bit adder lah. That means we have to combine two of 4-bit adder lah to be a 8-bit adder. Okay, something like this lah. You can see this one. This one we call the adder expansion lah. So adder can be expanded to handle more bit by cascading. So for example, if we have another 8, so we have another okay, so another 4 here, and then another, for example, we have 16. Okay, for 16 bits. Okay, for the bit normally we have 1 bit, 2 bit, 4 bit, 8 bit. Okay, 16 bits, 32 bits, and so on. Okay, that means power of 2 power of n. Right, 2 power of n. So this one we have 8 bits, so we have 16, so we have another 2 of 4-bit adder. Okay, 4-bit adder here. Okay, this is some example. Okay, some example here. Right, so for example we have okay, 10111001. So plus with 100111110. Okay, so actually the operation here you are study on the numbering system, isn't it? So you already study on the numbering system. Now for chapter 3, you see how this numbering, okay, this adder will be processed in the IC lah, in the digitals. So that means here we have the adder, so we use the adder, right, to implement this operation lah. So for example, in our topic 1, we just focus on this one. For example, 1 plus 0 will be 1. Okay, no carry. So 1 plus 0 plus 1 will be 1, no carry, and so on. Okay, so you can see this one on the first topic. Okay, topic numbering. All right, so I think this one is not to do, but we have to know how to implement this numbering system lah. So we have to use the cascading of the 2-bit adder to form the 8-bit adder. All right, so this is the system lah on the digital lah, actually something like this. Okay, so here will be okay, actually our C0 is the ground lah, because C0 is equal to 0. Equal to 0, that means everything is 0, we put to the ground lah. And then this output, okay, will be input for second. Okay, for second full adder here. Okay, for adder here. So similar like this one. So if you have another adder here, so also similar like this lah. So for example, we have 16 bit. So this one another one lah. Okay. Then this is the input. Okay, actually this is the input, this is the input. Okay, and then this is the output. This is the output, this is the output, you can see. All right, so this is we call the least significant bit, and this one is more significant bit. Make sure you read from the make sure you have to know lah which one the least significant bit, which one the most significant bit. So for example, here we know, so this one is the least significant bit, and this one will be more significant bit. Right. Right. So this is some example. Some example. You can see this one. We have cascading that I mentioned to you. So cascading of 4-bit 4-bit adder to form a 16-bit adder lah. So this one. So this means we have 4-bit adder. We have another 4-bit adder, 4-bit adder, and another 4-bit adder lah. So it actually come from this one. You have to read. Okay, so this is the least significant bit, and this one is the most significant bit. This is the output. Okay, this is the output, and then this is the input lah. So you put the input, and then what is the output lah, right? So maybe the operation we can do similar like the similar like chapter 1 lah, the operation on the adder. Okay, so next is the parallel subtraction using the parallel adder. Alright, so the parallel adder used to perform the subtraction A minus B using the second complement system. Okay, so hopefully you don't forget the second complement. Second complement system. The second complement system, first you have to convert into first complement. That means you have to invert the input. Then we have to plus with 1 okay, at the least significant bit. That is for second complement second complement that we call it second complement for to change this one to change this operation to be a plus to be a positive, okay, to be a positive. So that's why we used to use a second complement. To use a second complement, first you have to remember you have to invert the input, okay, using the first complement. Everything input you have to invert, then plus 1 at the least significant bit. So that's we call the second complement. Okay, for the bit of the subtrahends, okay, B are inverted, carry in, okay, is equals to 1 to produce the second complement. Okay, the design subtractor using the parallel adder as shown in the figure below. So this is okay, you can see this one. So this one we call the right. So this actually is the first complement. First, so you can see actually this is inverted. Okay, we have the before this we have the B. So we invert. We invert because we want to okay, to do a second complement, and then the carry out here will be plus 1 So that means you have to remember so the second complement we have to do the first complement is invert the input, and then plus 1 at the least significant bit. So this one we call the to produce the second complement right. So this is the parallel subtraction using the parallel adder right. So you can remember so for example, okay, this some example just refresh on the first chapter. So we have simple example right. So the first, okay, so this is this system we need to convert into the second complement. For example, second complement. So this is process for second complement. For the first complement, we have to invert the inputs, okay, and then for second complement, you have to plus 1 Okay, so 0, 1, okay, 1, 1, 0, 0. Okay, so actually this is the output. Similar like this, okay, similar like this one. So you can see first the invert the input here, and then plus 1 at the C naught at the we call the least significant bit Okay, so this one we call the second complement. Okay, next. So next is the ripple carry adder. So ripple carry adder is one in which the carry output of each adder is connected to the carry input of the next higher order stage Alright. So on the sum and the output carry of any stage cannot produce until the input carry occur So this cause the time delay in the additional process. Okay. So actually you can see this one every process. So that's why you have to remember, so the disadvantages of the digital is the time delay, right? So remember, the disadvantages of the digital is one is the world is the analog, and second one is the delay So delay. So every process from this one, okay, this component to this component, they have the delay. Okay, that's why we call the carry propagation delay. Yeah. So you can see this one. So from this carry, so we have 8 nanosecond delay here, and then every process we have nanosecond here. So that's why you can see the total delay for this system we have 32 nanosecond. Where actually is a nanosecond is very fast, but still have the delay compared if you use the analog. Analog is a straightforward. If you use the you can implement and then straightforward you can get the result For example, but for digital it will be every process. Okay, for example, every process from this header to another header to another header, they have the delay Okay, you can see this one from this one to this one we have the 8 nanosecond. Okay, 8 nanosecond, and then total will be 32 nanosecond So this one we call the propagation delay. Okay. Okay, next we go for the comparator. All right, so comparator is the basic function of the comparator is to compare the magnitude of two binary quantity. For example, we have the quantity A and quantity B. So we have to compare either this number is equal or not. Okay, for example, like this one. So equality. Okay, so equality we use the exclusive NOR. The exclusive NOR can be used as the basic comparator. Alright, so as maybe you have to remember for exclusive NOR truth table So for example, if the input will be same, so the output will be 1 Okay, for example, the input will be same. For example, 0, 0, the output will be 1. Okay, for example, 1, 1, okay, the output will be 1. If not same, so the output will be 0. That is the truth table for exclusive NOR. That's why we can use the exclusive NOR to use as the basic, okay, as the basic comparator to compare two digit So example, here we have digit A, and then this one will be B. So we have to compare. We have to compare whether this A and B is the same or not. So this one, for example, A is a 0, B is a 0. So automatically the output will be same. Output 1. So automatically we know the input A and input B are same. Okay, same equal same equal. Right. For example, like this one we have A is the 0 and then B is 1. So automatically the output will be will be 0. Then we know the input is not same. The input is not same. Similar like this one Okay. So but if okay, A is 1 and B is 1, so automatically the output is 1. So we know the input will be same. Okay, so to compare the equality of 2-bit binary number, so additional exclusive NOR gate is necessary right? So you can see this one exclusive This is similar like before this. Okay, so I go for the example. All right, so this is some example. So this is actually you can see this one compare A and B. Determine the comparator output equal or not equal. Okay, for example, for A we have 0, 1. We have 0, 1, and B we have 0, 1. As you can see here, actually you can see actually from this one we know. So the both actually is the equal right? You can see because of on the first inspection So this one is a 0, 1, and also this one is 0, 1 Okay, this one is a very simple. But if you have, for example, like 16-bit or we have a 32-bit, so that's why we have to compare. Is it for A and B is it the same or not? That's why we need some comparator For example, this one is just 2-bit. That's why it's very simple. You can see. So this one you can see. For example, you have I mentioned you have 16, something like this, something like this. Okay. For example, this is you have 16-bit. So another one, this is for A, and then for B also almost, but we don't know which one on the location of the 0, for example, but almost same, but the location of 0. So you can use the comparator to compare this binary this binary for A and this binary for B. As you can see, it's almost similar if you see the first time. So from there you can see, but for example, like this one also, we have 1, 2, 3, 4, 5, 6. Okay, this one 1, 2, 3, 4, 5, 6, 7. Okay, on the 7 will be 1. For example, it's quite different. So that's why we need some device or some comparator that we use comparator to compare the input. Is it the same or not, or equal or not equal Alright, so this one is very simple, simple example. For example, this one we know. So A is a 1 1, and then B is a 0 1 lah. You can see the first thing you know, so automatically we know. So this is actually it's not equal. But on the theoretical, we have to prove like this lah. Alright, we have to prove like this. So 0 0. Okay, for example, the A, okay, 0 0. This one will be 1. Okay, 1 1 will be 1, and then using the n 1 1 will be 1. So this is called the equal. For example, for second, for B, you can see this one. Okay, for A, 1 1. Okay, A 1 1, B 0 1 0 1. So this one will be 0, and this one will be 1. Then using the n, so n will be here. The output will be 0 lah. 0, that means the input A and B is not same lah. Okay, A and B is not same. That's why we use the exclusive no to do a basic of the comparator lah. For example, this one is very cheap. We used only 2 bit, but we have 16 bit, we have 32 bit. That's why we have to compare using the comparator, so that the binary A and binary B is it equal or not equal. Okay, this is some example. So only 2, but for example like this. Okay, maybe you can, the first thing you can see is almost similar, but it is same or not equal. That's why you can use the comparator to do the comparator between the A and B. Is it same or not same lah. Alright, so and next we go for the inequality. Okay, so many IC comparator provide additional output that indicate which of the two binary number. Okay, let's say we put as the A and B being compared. So we just compare A and B. So you can see we have 3 conditions actually. Okay, we have 3 conditions. Okay, this is condition. Okay, first A and B is equals. Okay, A and B is equal. Second, A greater than B. Third will be A less than B. Okay, so that's mean on the inequality we have 3 conditions. First we have the A equal than B. Second, A greater than B. Third, we have the A less than B lah. For example, like this. Okay, you can see this is actually is a. You can see the symbology of the 4 comparator lah, 4-bit comparator. Right. For example, this some example here. Right. So we have 0 0 1 1. Okay. So this one we have 0 0 1 1. Alright. So when we compare this one, actually this one will be A equal with B. So the output will be here. So this is the 1, and then this one, okay, so will be 0 0. So the output will be 1 here. Alright, so this one will be 0 0 lah. So the output on this one lah. Okay, for example, in another example we have okay, so in another example we have 0 here, and then we have 0 0 1. Okay. Now we know. So now we know B greater than A. Okay, that means A less than B lah. A less than B. A less than B. So that means our output will be 1 here, and then the rest will be 0 lah. So here this output. So this one we call the 4-bit comparator, right? To compare, okay. So first we have to compare, then we put some situation lah. So for example, if A and B is same, so this is the input, okay. To activate this one, this trigger this A and B equal to B. Okay, but for example, this one A less than B, that means B greater than A, so we trigger this one lah. For example, that means the will be activate lah. This one will be activate, will be 1 lah. Okay, will be activate. Okay, for example, like this. So this is some exercise. You can see this one. Alright, so okay, for example, this is the input. Okay, 0 1 1 0. Okay, this means here will be 2 plus 2 will be 6. Okay, for example, this one 3. Alright, so we know A greater than B. A is the 6 and B is the 3. So we know A greater than B. So this is the output lah. You see, that will be high here. So we will activate this one at this point. So the rest will be low. Okay, this means here is high, and then the rest will be low lah. So this is the function of the comparator. Okay, for example, we have some in that example we have 0 0 1 1, and then we have a 1 1 0 1. Okay, so that means here we know. So this one we have the 8 plus 4 we have 12. This one we have 13. So you know A less than B. So this one will be high. Okay, this one will be 1. This rest will be 0. Okay, the rest will be 0 lah. Okay, so this is you can see this is the IC, on the comparator lah. So they use this IC lah. So when you look at the IC name, the IC name. So for example, like this one 47H C885. Okay, this we call the comparator. Okay, the comparator lah. So we can use the comparator. So inside this one like this lah. So actually this is the I mentioned to you. Okay, so this starting here. So you can see lah the which one the input, which one the output. So it's not sequence like this. So they have the, for example here, you can see the input here actually is the leg for the so this is the input, okay, for leg 10. Okay, that's why you know. So this is the input A0. Okay, input 1. Okay, you can play input 1. So 12. Okay, so this is number 2. All right. So and then number 3 and then 15. So 15, which one? Okay, this one number 4. Okay, this one sure, this one for A. All right, so this one for A, input A, and then for B here. So for B here, so that's why you have to refer the diagram lah, the pin diagram. So normally it's not equal, the numbering is sequence. So 1 2 3 4 5 6 until 16 will be same, but the function of every leg will be different. You have to refer the pin diagram and logic symbol lah. So from this one you have to know lah. So this one we know. So the output here, okay, for example, this you can use the output here, okay, or you can use the output here, right? So this is for input, actually for cascading, but that means if you want to compare more than 4, okay, we can put another one here lah. For example, we put another one comparator here. So that's why here, so for example here we can cascade with this one, right? So this is another one lah, another 4 here, and then this another one. Okay, this one we call the cascading lah. That means if more than for example, if we have 8, okay, 8 bits, okay, 8 bit, we have to compare with 2 IC. We have to use these two IC lah. Okay. All right. So this some exercise as that mentioned to you. Okay. So for example, we have the two 8-bit numbers. We have 8-bit numbers lah. That means we have to use two okay, to 4-bit, okay, for 4-bit lah here. So this one, the how it's connect lah. So you can see this one will be cascading to IC1 to IC2. Then this is the output. Okay, this is input, and then this one will be okay. So that's why you can see. So this one will be we have the supply and we have the ground. Okay, make sure. So will be this IC will be on lah. Will be on because we have put supply here. So if we don't put any supply here, so this comparator cannot function cannot be function. That's why we have to put the VCC that we call the VCC and the ground. All right, so this is some example. Okay, you can see example 1. Okay, right. So figure below show the block diagram of the digital system which compare 2-bit binary. This means we have the A0 A1, and we need to compare with B0 and B1. So you can see A and B are decimal value. So A1 and A0 are binary representation of A. So whereas B1 and B0 are binary representation of the B. So the input A and B are more significant bits. Okay, MSB, and then the system is high. Okay, you have to read this one. The system is high. That means will be the output will be 1. The output 1 when A greater than B. Okay, when A greater than B. Okay, that means A greater than B lah. So that's why first we have to do the lookup table lah. All right. So you can see the first we have the first step you have to do the lookup table lah. For example, we have this one A0, A1. So actually we have here actually we have the 4 bit. Okay, we have 4 input lah. That means 2 power of 4, we have 16. That means from we have the 16. Okay, we have the 16 lah, sequence lah from 0 to 15. Okay, so this is in the decimal. So this is in decimal. Alright, in decimal. So 0, 0, 0, 0, 0, 1. Okay, so this one you can split by 2 here. Okay, alright, so you can compare. So you can compare A greater than B. Alright, so this one, okay, you can see which one there's one here. So A, this one, A not A or A called the A greater than B, because this one 0, 0 and this one 0, 1. So A greater than B, so the output will be 1. Okay, the rest will be 0 lah. For example, this one 1, 0 and 1, 1. So A greater than B. So 1, this one 1, 0, 0, 1. So A greater than B. So something like this. Okay. Then from this one you can write the boolean apa. Also you can use the K-map, or you can use the the expression. Okay, for example like this one. Alright, so this one is come from, okay, for example like this. Example like this one. So for example we have the here. I put as the A. Okay, put a A1, A0, okay, B1, B0, bar. Okay, something like this. Okay, and so on. Okay, so this one is the original lah. Original come from the truth table here. Okay, so that means we have one here, another one here, another one here, another one here, another one here. So that means we have 1, 2, 3, 4, 5, 6. Okay, we have 6. Okay, we have 6. So that's why we have to use the K-maps. Okay, we use the K-map lah to simplify the output Boolean expression lah, or Boolean algebra using the K-map. Or you can use the rules or De Morgan, alright, or you can use the K-map lah. For this one, I suggest to use the K-map lah. For example, if you do the K-map, so we can get like this, something like this. And then at the end we know, so we have to circle this one. So we have to know this one lah. We have the 1, 2 and 3. So this is the last one lah, the simplified. And then from this one we can draw the logic circuit lah. We can draw the logic circuit. So this one will be covered on the chapter 2 lah. That's why we have the Boolean algebra or Boolean expression. So we have to draw the logic circuit lah from this Boolean from this simplified Boolean algebra. So you can get like this lah. Okay, so this is a simplified F to design the comparator lah. So this is the comparator. This one inside the comparator lah. Okay, compare, then we use this one. Okay, we use this one. So the original one here. Alright, so we have too many. Maybe we have a lot of digital. We have a lot of logic gate. Then we simplify, so we can reduce the number of the logic gate lah. So maybe we have only 1, 2, 3, 4, 5, 6. Okay, we have only used 6 gates lah, logic gate. So compare, then if you use the original maybe 10 or 12 or I'm not sure. So we have more than this. So that's why we have to simplify this Boolean expression to get the simplified circuit lah, to reduce the number of logic gates. Okay, next we go for the decoder. Okay, so decoder. Alright, so decoder is a logic circuit that accept the set of input that represent the binary number and activate only the output that corresponding to that input number lah, and then the rest remain inactive. Right, so as you can see, this one, the input n is the bit codes, so output is the n 2 power of n. Okay, you can see this is a figure here is the 4 line to 60 line. So this is the input and then this is the output. Okay, this one we call a 4. Okay, 4 input line, and then we have 16 output line. Right, so we call the binary coded decimal to decimal decoder with active low output. So this one is the active low lah. This one So we have bubble here. We call the active low. So if active low here, alright. So you can see if active low. Okay, so if first step maybe you can check on the enable. So this one we call the enable input lah. So enable input. So if you have bubble, that means this is the active low. So the active low you have to remember. So the active output line is a 0, okay, and then the rest will be 1. The rest will be 1. If active high, that means if no bubble here. For example, if T here, so no bubble here, so automatically we know this is the active high. So active high, that means the output is 1, okay, the output line is 1, and then the rest will be 0, right? So okay, you have to remember this one. So maybe you go for the example here. Okay, so this is how example inside this decoder. So this one some example inside this decoder lah. So we have 4 input here, all right, and then this is 16 output here lah. So you can see, so this is the enable lah, G1 G2 enable gate. Okay, so this is the IC. You can see we use the IC as a decoder. All right, so I will show some example here. So you can see this one. So you can, so this is active low. So that means if the output here will be 1101. So 1101 actually is the this one 8 plus 2 plus 1 so 11 so the output will be 11. So on the 11 will be 0 active low. All right, so the rest will be 1. Okay, because this is we call the active low. Okay, that's why we call the active low, because of the enable is the active low. All right, so for example, if you use the active high, okay, active high, that means here will be 1, the rest will be 0 lah. All right, so if you use the active high, so now we use the active low. We use the active low, that means the output will be 0, the rest will be 1. Okay, the rest will be 1. Okay, so this is a example of the of the decoder. All right, so we use the 4 to 10 decoder lah. So this is some IC that we use for 7H C42, right? So this is the digital, okay, decimal digital from 0 to 9 until, okay, so this is a binary coded decimal code, and then this is the decoding function lah. So you can see it's similar lah. For example, 0 0 0 0. So you know this one will be 0. Sorry, this one will be A bar, A3 bar, A3 bar, A2 bar, A1 bar, and A0 bar. Alright, for example, then for example, like this one, we know this one A3. This one will be multiplied by A2 bar, multiplied by A1 bar, and then this one A0 lah. Okay, you can see this is we call the decoding function. Okay, so the function of this one, we want to do the 7 segment lah. Okay, to implement this one on the 7 segment. Okay, for example, like this one that I mentioned to you. So this one we use for 7 segment. Okay, you can see this one. Alright, so for example, actually this some example we just implement from 0 to 9 because we use the only one 7 segment. That means this 7 segment can display the number. Okay, for example, from 0 to 9. Okay, for example, if you want to implement 10, so we need another decimal lah, in another 7 segment display. So this one, that's why the rest here you can see this one, the rest will be don't care. Alright, this one you can don't care. So do not activate this one, don't care. Call it don't care lah. Alright, so until 9 lah, because of we use the only one 7 segment. Only one 7 segment can display from 0 to 1. Okay, for example, to display the 0, okay, we have to activate the segment A, B, C, D, E, F, but G will be 0, right? This so you can see this 7 segment actually something like this. Okay, so we have LED here. All right, so this is we got A. This one we have a okay, this one B. Okay, this one we have a C. This one we have the T. For example, we have a E here. So we have the F here, and then this one actually LED lah, something like this. Diode. We have diode here. Okay, I just and then this one will be G. All right. To display the 8. Okay, for display the 8 number 8. So this means all will be 1. That's why you can see if we display 8, so all everything is 1 lah. Here, everything is 1. For example, we want to display 1. Okay, this one. That's why we have to on B and C. For example, number 1. Number 1, we have to display B and C. So you can see B and C here. B and C will be on, the rest will be 0. Okay, for example, number 4 here. Okay, number 4. So we have to active number B, C, F, and G. So that's why you can see on the number 4, okay, B, C will be active, and F and G. Alright, so this is the output on the 7 segment. As you can see this one. Alright, for example, for 9, okay, 9 we have another one here. So another one here. So we off on the E. That's why you can see on the E here for 9 it will be off. Alright. Okay. Okay, so this one we call the 7 segment. So if you want to implement the, for example, 10, so we have to put another one 7 segment. So 7 segment only can display only 0 to 9. Only 0 to 9. Okay, that's why this one we can put as the X or don't care. Okay, so this is some example on the circuit. Okay, so I can see this is diode. Okay, we have diode here. So we on the LED lah. So example, you want to display the 0. Okay, the 0 will be A, B, C, D, E, and F will be on. So G will be off. Okay, for example, for 0. Okay, and then this one is to protect our we have resistor here to protect our current our diode here. Okay, that's why here the function of the this resistor for current limiting. Current limiting. Okay, so this one we call the BCD to 7 segment. So this one will be important to you when you do the assignment. Okay, assignment using software, using the software. Okay, using the Portius, okay, using the multi-sim, up to you lah. Okay, so we have a lot of software to run the digital circuits. For example, like multi-sim, we have the Portius, okay, we have the PSpice, okay. So you can use this software to run the digital circuit lah. For example, like this, So you can run the 7 segment, okay, using the 7 segment decoder, right, and so on. After, okay, so the assignment will be discussed after Raya, after Raya lah. Another 2 weeks, okay. Alright. So this, any question? Alright. So okay. This one. Yeah, so I forgot to. Okay. Alright. Okay. So this some example of the decoder lah. Alright. So some example of the decoder. So from this figure, write the Boolean expression for X and Y as the function of the inputs A, B, C, and D in the standard SOP. Okay. And then obtain the simplified SOP express of X and Y lah. So this one, so this some example. Okay, it's come from this one, right? Okay, this one. Okay, this one. Alright. For example, if you have the 0, 0, 0, 0, so this one, this one you can declare as the 0, 0, 0 lah. Okay, 0, 0, 0, and then you can get the X here and Y here lah. Okay, so this is actually come lah. Okay, it's come the truth table for the 4-bit decoder. Okay, 4-bit decoder. Okay, so this is example 3. Okay, the specification of the required decoder is given below. So if the input A, B equals to 0, 0, then the number 0 will be displayed lah. So if the input is a 0, 1, so display number 1. If input 1, 0 will be display number 2. If 1, 1, display number 3. Okay, so we use the 7 segment for the communicated. Okay, communicated type. Okay, that means the logic 1 use to activate the 7 segment lah. That means we use the 1 to activate the 7 segment lah. First, we have to develop the truth table lah of the required decoder. Then we can use the K-map to get the Boolean expression. Then draw the circuit for every segment for each segment lah. Okay, for example, like this, we know. Okay, you can see this one. So this is the condition here. So if the input, input A and B is 0, 0, then will be display 0. Okay, for example, input 0, 0 will be display 0. So 0, you know. So on the 7 segment, so 1 will be on. Okay, only G will be off lah. For example, so that I draw. Okay, before this, so okay, so this is our 7 segment. So something like this. Okay, actually this is diode lah. So A, B, C, D, E, F, G. Alright, so you can see this one for display the 0. That means for input A 0, B 0. So to display the 0, so that means we know. So only G is the 0. The rest will be 1 lah. So that's why here will be 1. Okay, the rest will be 1, and then this is 0. Okay, next. Okay, next condition, you can see next condition is 0, 1 will be display 1. So 0, 1 will be display 1. That means you want to display 1, we have to on this part lah, BC. That's why you can see BC will be on, the rest will be 0. Okay, next will be display 2 lah. 2 will be like this lah. Right. Okay, sorry, like this. Okay, 2 like this lah. So that means will be on A, B, G, E, D. Right. That's why you can see here for 2, A, B, D, E, and G. So will be on. Okay, this means here will be A, B, G, D, A, E, D. Alright. Alright, and then last will be 3 lah. Will be number 3 will be displayed something like this lah. Number 3 like this. So will be A, B, C, D, G. Okay, so you can see A, B, C, D, G. Alright. So this is the truth table, and then you have to draw the K-map. Okay, the K-map you have to make sure. So the K-map every 7 segment, that means the first K-map here you have to map with this one. Okay, so you can see the 7 segment for A. Then next you have to get this input with this output. Okay, for 7 segment B here. Okay, and then next this one to C. Alright, until so on. So you can see, so for example here, just do the K-map here. So this one A and B. So 0, 0. Okay, 0, 0. A is 1 here, and then 0, 1, 0, 1. So it will be 0. Okay, it will be 0 here, and then 0, 1, 0, 1, 0 will be 1. Okay, will be 1, and then 1, 1, 1, 1 will be 1, 1 will be 1. So and then from this one you have to use K-map lah. So K-map maybe we learn before this. So we have to get the circle here. So 1 and 2, and then you can get the expression, the Boolean expression like this. Then you can draw lah. Okay, actually this circle for segment A, for segment A. And then for B, okay, for example B, you can get all the 1, so automatically, so this one will be 1, so automatically is from supply. So if the output 1, so automatically to supply 5 volt. Okay, to supply. If 0, to ground lah, to ground. So that is the symbol. If 0, that means go to ground. If 1, go to you have to supply lah, VCC. Okay, or you put the 5 volt here. So you can see this one for segment B, and then you can see C will be like this, and then you can get the the logic circuit like this. Then you can continue so on. Okay, you can see for example, if you get A, alright, so this one will be inverter. Okay, and then you can combine lah. You can combine into one circuit. Okay, this one is some example lah. For example, using the decoder, using the decoder. And then you can combine everything from the segment segment A until the segment G. Okay, that is the combine into the circuit lah. Okay, right. So next we go for the encoder. We go for the encoder. Actually, the encoder reverse lah. reverse of the decoder function. Okay, so the encoder is the combinational logic circuit that essentially perform a reverse decoder function. So before this we study about the decoder. Now encoder is the reverse of the decoder function. So the process of converting from familiar symbol or number to a coded format is called encoding lah. Okay, encoding. Okay, this one. Okay, so this is our input, and then this is the output lah. Alright, so for example, from our 7 segment, okay, to get the output lah in the binary, for example, like this. Okay, so for example, our digit, digit is 0, so that means our A, B, C, A3, A2, A1, A0 is a 0, 0. So this one is a standard lah, standard like a truth table lah, from 0 to 9. Okay. This one actually is come from the 7 segment, from 7 segment. Okay, so maybe we go for the example. Alright, so we have to design the binary encoder with priority. So the description of the required encoder is given below. Okay, so A is the least significant bit. Okay, so that means here will be we set as the least significant bit, and then this one will be more significant bit. So you have to know. So A we set as the least significant bit, and B we set as the most significant bit. So you can see the normal case. If only A activate. Okay, so A is a 1. Okay, that means our XY is a 0, 0 lah. So for example, only this one only 1 here. Okay, so this one will be 0, 0. Okay, and then for B activate, if B activate, so will be display 0, 1 lah. Will be display 0, 1. If C activate, okay, then will be display 1, 0. Okay, for D activate, so will be display for the XY will be 1, 1 lah. Will be 1, 1. So this is the normal case. Okay, for normal case. Then for abnormal case, okay, abnormal case, if more than one input activate lah, that means maybe we have A and B activate. Okay, so A and B activate. So for example, this one so A has more priority than B. Okay, that means A we have to give a priority on A. So some same like this. B has more priority than C. We can put lah. So if you have C, B and C, that means we have to give a priority on the B. So if the C and D, so we have to give a C have the more priority than D lah. Okay, for example, if the both A and D are activate, right? So the XY will be displayed like this one lah. Okay, because of the C will be priority lah. So for example, this one okay, for example, activate is 1, 1 1, 1 this one is 0, 0. Okay, so as you can see, this one will be activate 1, 1. So that mentioned here. So C is more priority than A, more priority than D. So this means is like 1, 0. That's why 1, 0. Okay, so that's why here will be display 1, 0. Okay, 1, 0. Okay, so another case, if no input, okay, no input is activate, so XY will be put as the X lah, don't care. Okay, Y and then we put as the don't care. Okay, so we have to on the don't care, we have to put the truth table on the required encoder, then use the K-maps to get the Boolean equation for each of the segment X and Y. Alright, so this is some example lah. Okay, so we develop the truth table. Okay, actually from this one from this condition here. Okay, from the condition here, so we develop the truth table. Alright, so you can see this one. Okay, why we put X here? This is don't care. So you can see if no input activate, that means A, B, C, D no activate lah, will be 0, 0, 0, 0. So that's why here will be X. Okay, you can see on the case number 3, this one if no input activate, that means A, B, C, D, no input lah. This means will be 0, 0, 0. So will be don't care. The rest will be, you can follow this one lah. For example, if activate, so XY will be 0, 1 lah. Okay, so you can see this one. So 1, 0. Okay, 1, 0. That means A will be activate. A activate. I put one example here. A activate. This means 0, 0. Okay, you can see this one. 0, 0 will be activate. That's why XY will be 0, 0. Okay, then next you can see this one. B activate. Okay, B activate will be 0, 1. Okay, will be 0, 1. So here you can see will be 0, 1. All right. Then if you put the the A and B will be activate. So we priority on the A. You follow the A. So that's why you follow the A will be 0, 0 lah. So that's why you have to refer this case. Okay. So A has more priority than B. So that's why we follow the A lah. Alright. So that's why here will be 0, 0. And you have to put until from 0 to 15 lah. Because we have 4 variable input. Okay. 2 power of 4. We have 16 sequence from 0 to 15. So you can get the X here and then the output for Y. Then from this one, you have to develop the payment for this one first. Okay, and you can see this one. And then another one here, the input with the output for Y. Alright, so you can see this one. So I put here. Okay. Alright, so for example, we get like this. So as mentioned before this, the X, the don't care will be advantageous. Okay, we will use if we can we can upgrade the number of circle. Okay, for example here actually we can so now we have 3. So that mentioned to you, we have to increase. Okay, we can increase this one per priority more circle lah, more for example the priority is the highest circle. For example here we have 16. The first priority you have to go for 16. Then if cannot you cannot settle the 16, you have to down to 8. If not 8, so you down to 4. Okay, down to 4 cannot, so down to 2, and last is the down to 1 lah. For example here, so X this one actually we can grouping for the 4, so that's why X can be we can declare as the 1 here. So that's why you can put here group 1 grouping here. So the output will be A bar, B bar. Okay, A bar, B bar. This one, right? So next for the Y. Okay, for the Y. Okay, so you can see this one. So similar like this one. So we can use this X advantages for we grouping for the 4 here. Okay, this one 1, 1, and 1. Okay, you have to remember. So actually this can share together into one group. Okay, because of this gamut is like the spherical lah. That means this this point actually is connect to this point and also connect to this point and also connect to this point lah. This is like the spherical lah. Also if we have here and also we can connect to this one for example. Okay, so why you get like this lah, A bar B and A bar C bar, right? Then you can draw the you can draw the skirt lah from the, for example you can draw the encoder lah. Okay, based on this expression this expression you can draw the circuit. Alright, so I think okay, multiplier I think I stop here because okay, I will stop here. So the multiplier I will start on the after Raya, I think. Okay, because next week we are focused on the midterms. Okay, so next week we have no class. Okay, on the Thursday and Friday. All right, so next week we don't have the class. Okay, because we have to focus. Okay, you have to focus on your midterm on the 6th. Okay, 6th May on the Thursday. So on the Thursday evening, I give your time to study. Okay, to study this subject, so no need to class, right? But if you have any question, you can okay WhatsApp me, so we can discuss okay through WhatsApp. Okay, if you have any question, all right. So and then also on the Friday we don't have any class. Okay, on the Friday, right? So and then another weeks, okay, we have the Raya on the Thursday and Friday. So also we have a holiday, so we don't have the class lah. So we continue our topic will be on after Raya lah. After Raya, I think 2 weeks from now lah. 2 weeks from now, we continue on the multiplexer. Alright. So so far, any question? Alright. So for the tomorrow, okay. For tomorrow, as you can see here, alright. So you can see my YouTube here. Guys, can you see? So actually I already scheduled for my video. All right, so we have two tutorial. Okay, we have two video for tutorial 2. It's a part 1 and part 2. Okay, so we'll be scheduled on this one will be scheduled on 8, okay, 8 a.m. okay, for tutorials part 1, and tutorial part 2 part 2 will be on schedule on the 9, okay, 9 a.m. lah, 9 a.m. okay. So that's why tomorrow you can watch the video lah. But for this tutorial that I mentioned to you, but this tutorial you can watch anytime. But make sure don't forget to write your comment as your evidence lah. So as evidence to for me to take as evidence. That means you already watched this video and already see the tutorial lah. So if you have any discussion on the tutorial, so you can discuss. Okay, you can you can WhatsApp to me. So for example, maybe I do some mistake on the solution. I'm not sure. So maybe you can discuss through WhatsApp. Okay. All right. So I think that's all for today. Okay. All right. Tomorrow we don't have a class, so just a video for tutorial 2, part 1 and part 2. So you can watch this video tomorrow. Okay, at 8 a.m. and 9 a.m. It will be 8 and 9 a.m. All right. So if no question, I will stop here. All right. So we'll be